I've broken my stoichiometry notes, which would be chapter 12 in my textbook, uh, down to three basic steps here. So I've broken this down into three little short movies. We're going to look at simple stoichiometry. So one step, use the mole ratio. That's the first one. It's just simple stoichiometry, one-step stoichiometry. Second set of notes is going to get into multi-step stoichiometry, where we look at more complex stoichiometry situations, but it's still stoichiometry because we're still using the balanced equation. And then the third set of notes deal with limiting reactance stoichiometry because that's really an application of stoichiometry. So the first one here we're going to look at is using the balanced equation in a simple way. So first, before we get into simple stoichiometry, what is this weird looking word stoichiometry? Well, stoichiometry is a study of quantitative relationships between amounts of reactants used and products formed by a chemical reaction. A chemical reaction is like a recipe in that it shows the relationships between the different ingredients and your product. The difference in a recipe is you can change the ratios and still get it to maybe work out properly. The difference is a balanced equation is etched in stone. If the reaction says 2H2 plus 1O2 is going to make 2H2Os, that's exactly how that reaction happens. And therefore, there is a quantitative relationship between the amounts of each reactant that gets used and how much product is going to be formed. And we're exploiting those quantitative relationships in any stoichiometry problem. What makes stoichiometry stoichiometry and makes it different from questions in any other chapter is we're always asking information about one substance and you're going to be given information about another. All of the other math relationships we've looked at in our different dimensional analysis problems have all been dealing with the same substance. Stoichiometry is the first time we're going from one substance to another substance, and that's what makes this stoichiometry problem. So it's really about understanding the relationships in a balanced equation. Now, what does 2H2 plus 1O2 makes 2H2O really mean? Well, from a particle standpoint, it means you'd have two molecules of hydrogen reacting with one molecule of oxygen to make two molecules of water. And this isn't etched in stone the only way this can happen. So you have to have twice as many hydrogen molecules being consumed or used as you have oxygen molecules being formed. And guess what? You're going to get the same number of water molecules as you actually had hydrogen molecules. Now that's what it means from a particle standpoint. What does it mean from a mole standpoint? Well, it means 2 moles of hydrogen will be consumed or used for every 1 mole of oxygen that's used, and you're going to make 2 moles of water. And remember, what this fundamentally means is etched in stone. We have to use twice as much hydrogen as oxygen, and we're going to get an equal number of water molecules made as hydrogen molecule used, or twice as much as we had of oxygen. Now, which one of these relationships is more useful? Well, remember, particles are incredibly small. We never really deal with a particle amount. So that's why we changed when we were looking at formulas and molecular formulas, empirical formulas. We looked at those as ratios of moles because the mole amount is a much more workable, useful, everyday amount. We never really deal on the particle level because it's just too small. Now we also sometimes deal with masses. So how many grams of hydrogen for how many grams of oxygen? Would it be true that it's 2 to 1 to 2? So 2 grams of hydrogen for every 1 gram of oxygen would make 2 grams of water? No, absolutely not true because remember, each atom weighs differently. So hydrogen atoms weigh differently than oxygen atoms. So how would this work? Well, remember, we just said on the previous slide that, this equation says 2 moles of hydrogen. Remember, H has a molar mass of 1.0, so H2 is 2.0. Well, if we have 2 moles of H2, that would be 2 times 2.0. That'd be 4.0 grams of hydrogen. So if we had 4.0 grams of hydrogen, how much oxygen will we need? Well, 1 mole of oxygen. Remember, O is 16.0 per mole. So if we have O2, that would be 32.0 grams in 1 mole. So 1 mole of O2 would be 32.0 grams. Now, water, H2O. Well, we've said a whole bunch of times in here that the molar mass of water is 18.0 grams per mole. Well, if we have 2 moles of water, that would mean 36.0 grams of water. And notice, 4 plus 32 is 36. What scientific law does this actually illustrate? Well, that's the law of conservation of mass. Remember, these amounts are etched in stone. If we had 4 grams of hydrogen, we would have to have 32.0 grams of oxygen react with it. Otherwise, we wouldn't use up all of the hydrogen if we had too little oxygen. Or we wouldn't use up all the oxygen if we had too little hydrogen. And we'd get 36 grams of water from that. So if we used up 4.0 and 32.0, should make sense that we should get 36.0 because we can't create or destroy atoms in ordinary chemical and physical reactions. So that makes sense based on law of conservation of matter. Now, like a recipe, because I mentioned equations are like recipes earlier, the balanced equation tells you in what ratios the ingredients must be mixed. There, for every 2 moles of oxygen, you will need one, I'm sorry, for every 2 moles of hydrogen, you will need 1 mole of oxygen. Mathematically, that can be written as this equality because we're using up 2 moles of hydrogen for every 1 mole of oxygen. So in terms of this equation, this reaction, it would be true that 2 moles used of hydrogen is the equivalent of 1 mole used of oxygen. So those 2 moles equal those 1 moles. Well, every single time in chemistry we have had an equality. What have we done with it? Well, we've done dimensional analysis. So we've used inequality as a ratio in a dimensional analysis problem to convert from one thing to another. So that means this relationship means we can convert from moles of hydrogen used to moles of oxygen used, or vice versa. Because remember, every one equality gives us 2 different mole ratios or 2 different conversion factors. So 2 moles of hydrogen equals 1 mole of oxygen. Well, this type of quality is derived from the balanced equation above. And what we're really looking at is a ratio of, or an equivalency of 2 moles that can be written as a ratio of 2 moles of hydrogen over 1 mole of oxygen. So the mole ratio that's shown above, that equivalency between hydrogen and oxygen must be in units of moles, and our numbers must come from the balanced equation. So since every problem deals with going from one substance to another, and the only equality that we have that deals with one substance and another is a equality between moles. The only way to get from one thing to another is through mole ratios. And that's what makes stoichiometry stoichiometry. Every stoichiometry problem is going to have a mole ratio conversion factor somewhere in it. Now, how many conversion factors, called mole ratios, can be derived or written from the above equation? Remember, every single equality can give us 2 different conversion factors. So what are the different equalities? Well, we looked at the relationship between hydrogen and oxygen. We've got 2 moles of hydrogen for every 1 mole of oxygen. So that one equality is going to give us these 2 mole ratios. Well, that's not the only equality. We just compared this substance to that substance. I could also compare hydrogen to water. And then finally, I could also compare oxygen and hydrogen. So I really have 3 different equalities in this relationship. It would also be true that 2 moles of hydrogen equals 2 moles of water. So that would give us those 2 different conversion factors. And it's also true for every 1 mole of oxygen, I make 2 moles of water. And that one equality would give us 2 other conversion factors. So if we have a balanced equation with 3 substances in it, we actually have 6 different tools we can use. If we want to convert from one thing to anything else, I have 6 different tools to let me do that. If we had 4 substances, I'm going to get a lot more than 3 equalities because every substance can be compared to another. So we're going to get significantly more than 6 mole ratios if we have 2 reactants and 2 products. Now here is a typical simple 1-step dimensional analysis stoichiometry problem. How many moles of oxygen are needed to react with 6.4 moles of hydrogen? Notice they're asking me to go from one substance to another. I'm going from amount of hydrogen to amount of oxygen. So since I'm going from one thing to another, that's stoichiometry. Well, why is it 1 step? Because remember, my balanced equation is dealing with 2 moles to 1 mole to 2 moles. They're telling me ratios of moles. So if I'm in moles and asked to find moles, I can do that in 1 step. So here's how the problem would look. I've got 6.4 moles of hydrogen, and I want to know how many moles of oxygen I have. And I set up my typical workspace for a dimensional analysis problem. Well, I don't want moles of hydrogen. I want moles of oxygen. So I know I want to cancel out moles of hydrogen. That's going to go on bottom. I know I want to convert to moles of oxygen, so I'd put that on top if I knew an equality between them. Well, what do you think a balanced equation gives me? It says for every 2 moles of hydrogen, I need 1 mole of oxygen. So if I'm using up 6.4 moles of hydrogen, I would need exactly 3.2 moles of oxygen to do that. So when you're going from moles of one substance to moles of another, you can always do it in exactly 1 step. And they're all different variations of the exact same thing. They're all going to be 1-step problems. The key is, notice they're giving me moles and asking me to find moles. If they do that, I need a balanced equation, and I know I don't need much room for work because it's going to be a 1-step problem. Now, here's another one. How many moles of H2O are produced from 6.4 moles of hydrogen? Now notice they're giving me information about hydrogen, but asking me information about water. Give it a try. Set it up. So pause this movie right here. Try this problem to see if you can do it. Okay, solution to this. I know I've got 6.4 moles of hydrogen, and I know they're asking me for moles of water. I don't want hydrogen, so moles of hydrogen goes on bottom, and I want water, so moles of water goes on top. Notice I'm always using two-part units. Get in the habit for everything in stoichiometry. Two-part units are critical. Never, ever, ever just put moles. Never, ever, ever just put hydrogen. It's moles of hydrogen, moles of oxygen, grams of oxygen, so on. Two-part units everywhere. And remember, my numbers for this mole ratio come from the balanced equation. For every 2 moles of hydrogen, I have 2 moles of water. So 6.4 times 2 divided by 2 is going to be 6.4 moles of water. And that ends my notes over simple stoichiometry problems.